So we are live now.
Hello everyone, welcome to this live session of digital system design. So yeah, before we start with the questions which you are raising in your YouTube live chat, I would be answering a couple of questions which we have received in email or using forum discussions. Okay, so I would be sharing my screen. One question which we have received, that how gray code is basically is represented. So this gray code is essentially such a system where individual, like the subsequent numbers are, there's only one bit of difference. So for example, there could be many such notations. But the notation which is very popular, most popular is, let's say this is called 0. Now to find 1, what do we do is 0, 0, 0, 1. You see the consecutive, these two numbers, there is only one bit is different, rest of the bits are same. Okay, for decimal number 2, the gray code looks like this: 0, 0, 1, 1, and for decimal number 3, the gray code is 0, 0, 1, 0. Okay, so you remember when we do K-maps, for K-map we essentially follow this feature, or basically this particular gray code, because adjacent rows or adjacent columns, there is a difference of only single bit. Now from 3 onwards, how do we go? Uh, for that, you just try to see that these two numbers 0 and 1, this is a kind of a mirror representation. Similarly, if we see here, except this 0 has become 1, otherwise a representation is a mirror representation. Okay, so in the same way, if I would like to make 4, what will we do? We will say that we'll consider these 4 numbers and we'll try to create a mirror representation where this bit will become 1, 0, 1, and the rest of the bits are same. Now we can start in a reverse way, the way a mirror representation looks like: 0, 1, and then this is 1, 1, so it is 1, 1, 0, 1, and 0, 1. So this mirror part came here, and similarly 0, 1, 0, 0. So this part came here. You see, this particular portion is mirrored. So this portion is mirrored here. Okay. Similarly, so this is the representation for 4, 5, 6, and 7. Similarly, we would like to go for 8, 9, 10, etc. So what we can do with the same formula will go here also. Now we will have this part will become mirrored, and here instead of 0 we'll put 1. So this would be 1, 1, 0, 0, and then 1, 1, 0, 1, 1, 1, 1, 1. For 11 it would be 1, 1, 1, 0, so on so forth. So you see, because we had to represent, let's say 0 to 15 using this 4 bits, then this would be the method. If we have to represent something different, let's say we want to represent BCD, that means only 0 to 9. In that case, we can choose a different representation. In that case, we require only 10 different codes. Okay, so but the basic principle should be that adjacent two numbers will have only a difference of 1 bit. Rest of the bit should be same. This is how we represent a gray code. Another question which I have received is to give little more like example and understanding of the shift operations. So shift means, let's say we have this number 1 1 1 0 0 1. So this is a 6-bit number. Now we can shift either in the right direction or we can shift in the left direction. If I want to shift in the right direction, so that means I want to shift in this direction. Okay, so when we are shifting here, then one bit will keep on shifted. So basically what would this one, this would be shifted, but there is nothing here, so we most likely would like to discard this. Okay, then this 0 will come here, this 0 will come to the next bit, this will come to the 1. Now this is 1, this is 1. The question is, what should be done here? What should we keep here? Okay, so this particular question gives us two choices, whether multiple choices actually, whether we can keep a 0 here or we can keep 1 or something else. How should we decide what should be kept here, 0, 1 or maybe something else? So let us see what would be the impact. If we are keeping 0 here, if we are keeping 0, what does it mean? So for that we have to understand how this number is represented. Now you remember that there are two kind of numbers, either it could be a positive number or it could be a negative number. If it is positive number, then all of these bits will have the same understanding or basically a same pattern. But if it is a negative number, then the MSB means sign bit. Okay, so MSB represents sign bit, so it has got a special property that most significant bit would represent 1. Okay, let's say the 6-bit number was a negative number. Okay, so in the case this was a negative number and we shifted it in the right direction and we kept 0 here in the most significant bit. So this number was a negative number. So a negative number became a positive number because now most significant bit we have kept as 0. So that would have a different meaning for certain cases. Okay, so that essentially means that it all depends whether this particular number was a positive number or a negative number. If it is a positive number, then the meaning would be that whatever this number represented, this right shift essentially means the number is going to be half of that. Let's see how it is. So 1 1 1 0 0 1. What does this mean? This means 1 plus 8 plus 16 plus 24. Oh, sorry, 32. That means 40, 46, 47. Okay, and if we see this 0, 1, 1, 1, 0, 0, what does this number mean? This means 4 plus 8 plus 16. That means it is 28. If you see, 28 is approximately half of 47. Correct. So this way, this particular number tells us that if we go for shift right and if we keep 0 here and we assume that this particular number is a positive number, then we can keep 0. Okay, MSB is 0. Okay, this means this is divide by 2, assuming number is a positive number. Okay, so this particular shift keeping MSB as 0 is called logical shift right. So this is called logical shift right because the number is assumed positive number. If the number is assumed as a negative number, in that case, this most significant bit has to be 1. This most significant bit should be the same as size whatever is the MSB in the original number. Okay, because here the original number was 1, have the MSB of 1, so this will also have a MSB of 1. This is called arithmetic shift right. In that case, we assume the number could be positive or it could be negative. So essentially, it's a of type integer or of its type of it's a arithmetic number. Okay. So that means the MSB represent a sign bit, and whenever we are shifting right, that MSB should remain same. If MSB was 0, then here we will insert 0. If MSB is 1, then we will have 1 in the shifted number. Also 1 would remain the MSB. This is what arithmetic shift right would mean. Okay, let's quickly look at the logical shift right. In case of logical shift right, logical shift left, sorry. Let's see the case of shift left. So in case of shift left, what we are doing, we are shifting in the left direction. Okay, so that means here this particular one will become here, this 0 will be here, and similarly this 0 will be here, and we'll have 1, we'll have 1. This particular one need to be discarded. Okay, what will come here? That would be usually 0. So because we are keeping 0 here, here there is no different meaning. If we have 0 or we have 1, there is no different meaning. So this is a shift left. So in shift left, there is no logical shift left or arithmetic shift left. It is always logical shift left. Okay, because even if the number is positive or the number is negative, so let's say this number would have been negative. So if this number is negative, then this is also this one bit says that it still remain negative. Okay, so what would be the cases? So basically this logical shift left essentially means we are dividing the number by 2. So here this was dividing, and logical shift left means we are multiply by 2. Okay, so let's look at some more interesting cases. If we say the number is this, let's say number would have been 1 0 0 0 0 1. Yeah. So and we are doing a LSL operation. So in case of LSL operation, this one will become, here we'll insert 0, and this is becoming this. Okay, so if it is if this number would have been a negative number, this would be some negative number, and this number is a positive number. So this is a negative number, this is a positive number. So does this case says that there is something wrong here? To understand that, let us look at what this negative number was. So if we see this negative number was, we have to take 2's complement, then add 1, we'll get to know what this number was. Okay, so if we say that, then we will get to know this number was 1 1 1 1 1. So that means this number was minus 31. If I multiply minus 31 by 2, then it would have been minus 62. Okay, however, this number is 2. This is clearly 2 plus 2. So am I doing wrong by discarding this one? Probably no, because minus 62 is outside the range of my 6 bits. My 6 bits can represent only the number minus 32 to positive 31. So because 62 can never be represented using this particular 6-bit range. So that is why it is okay to have one of the number as negative, and after shifting this number become positive. That means it's an overflow problem, but there is no problem with the overall operation of logical shift left. So in logical shift left, we would be shifting in the left direction. Whatever is the MSB, that would be discarded. In the least significant bit, we will insert 0. However, in shift right operations, there could be logical shift right. In logical shift right, we are discarding least significant bit, and in most significant bit, we are always keeping 0. However, in arithmetic shift right, we are discarding least significant bit, and in most significant bit, whatever was the most significant bit of the previous number, that would be copied again to the most significant bit. Okay, so yes, if somebody have any more questions or anything else to be discussed, please share your comments in the chat box. I would be waiting for a couple of minutes. If there is some question, either it could be related to course, or it could be generic also, or it could be related to some concept, please let me know and I would be happy to answer those questions. So in the meanwhile, I can discard sharing this, and yes. Since there is no other question, I think we can disconnect this session. And yeah, thank you very much. Good luck for rest of your assignments, as well as good luck for your exams. Hopefully, we'll have another live sessions in the next month. Thank you very much.
So